Exercise 318 is introducing the third factor that you want to consider when you're qualitatively assessing which hydrogens are most acidic. So that factor is something called induction. And remember, this REO rule of thumb is really a rule of thumb. There are exceptions to this. Not that I would ever give on a test, but in life there are exceptions to this. But in general with REO, first you want to consider the atom. Only if the atom ties would you consider resonance. Only if the resonance ties, the amount of resonance ties, would you consider this new factor, which is induction. And the idea here is that the hydrogen that has the most electronegative atoms the closest to it is most acidic. So for example, let's say you had this molecule here. So this is drinking alcohol. And actually, let me have this. And so there's this hydrogen here that can come off because the hydrogen, it's on an oxygen, which is electronegative, so that it can take the electrons in that bond, which would then be a lone pair with a negative charge, and it can stabilize it a little bit with its electronegativity. Pulls the negative charge close to the nucleus, where there's a lot of positive charge, and so helps to stabilize it. So that's a possibility. But if you wanted to make it even more acidic without using resonance, what you can do is you can take really electronegative atoms, and remember that electronegativity increases as you go up and to the right on the periodic table, so that the atoms in the top right are the most electronegative, and those are nitrogen, oxygen, fluorine, chlorine. Sometimes you'll see bromine. Those are the most electronegative elements on the periodic table. They're in that top right area. And what they do is they pull electrons toward themselves. So if you had a fluorine here, what that'll do is it'll tug. Now it mostly acts on this bond, as we saw in chapter 1. But it does act a little bit in this next bond. Not a lot, but enough to help stabilize it. Now it's not the biggest, it doesn't act a lot. It's the third factor here. It's only going to be relevant if the atom and the resonance aren't there. But it does pull electrons a little bit even from that distance, far away. And that helps to spread the negative charge out over more space. And again, the big principle that we'll see over and over again is when you have charge spread out, it stabilizes a molecule, and when you force charge into a small space, the charge repels itself, pushes against itself, it's very unstable. So the fact that you have this electronegative atom there helps to spread the charge out over more bonds. If you had more electronegative atoms, then it would spread out over even more bonds, even more atoms. And that would help to make this charge smaller and the molecule more stable. The more stable the molecule is, the more easily the hydrogen will get away. In other words, the more acidic it will be. So the more electronegative atoms you have, the more acidic it is. And also the closer they are. So if you compare that with this, if you had this molecule, same thing, but instead of two fluorines nearby, they're further away, that still will help to stabilize the molecule. It'll still help to bring that negative charge, spread that out over space, but because these are so far away, their pull on those electrons is much weaker. So it's very faint, and so it doesn't have as big of an effect. It doesn't have as big of an effect as when the electronegative atoms are closer. This would be more acidic, the hydrogen on that, and the hydrogen on something like this would be less acidic because the fluorines are further away, so the negative charge doesn't feel them. This negative charge doesn't feel them as much. Okay, so that's our rule. So here, it says identify the most acidic proton in each of the following compounds, and crucially, this question says explain your choice. Now they have two hydrogens, so first of all, there are lots of hydrogens in this molecule. All of the hydrogens are either on oxygen or they're on carbon. Right, all these hydrogens on carbon. Now, oxygen and carbon are in the same row on the periodic table, and the rule for the rows is that in a row, the hydrogen on the atom further to the right is more acidic, because that atom can stabilize the negative charge by pulling it close to the nucleus because it's so electronegative. So we don't have to consider the hydrogens on the carbons. We just have to choose between the hydrogens on the oxygens. Those are on the same type of atom, so the atom doesn't help us. We go to the next factor, resonance. Neither of these oxygens would leave behind, neither of the hydrogens on these oxygens would leave behind a lone pair involved in resonance. Imagine a lone pair with a negative charge there. That's not allylic, and it's not next to a positive charge, so it would have no resonance. And if this bond became a lone pair there with a negative charge, that also would not be allylic and would not be next to a positive charge, so it wouldn't be involved in resonance. So there's no resonance you would get if either of those hydrogens left. So resonance ties. So then we go down to induction, and we look for electronegative elements. And we see there are 3 fluorines here. Those are going to pull negative charge toward themselves. But it will do it more effectively if the negative charge is closer, because the electrons there will feel the pull of that fluorine more than electrons that are further away. And so the hydrogen here is the most acidic one, because if that hydrogen leaves, as it would if it were an acid, if it were acting as an acid, if that hydrogen leaves, then the oxygen is going to be left with a full negative charge, and that negative charge will be stabilized by all the fluorines pulling the electrons toward themselves. The effect of the fluorines would not be as large on the other oxygen if that were the one with a negative charge, because the fluorines are further away, so the oxygen, the negative charge there on this oxygen doesn't feel them as much. In other words, if we follow our rule, the hydrogen that has the most electronegative atoms nearby is the most acidic, and that hydrogen is this. It has the most electronegative atoms nearby. Following the same rule here, we have hydrogens on carbon and hydrogens on oxygen. We saw that oxygen will be able to stabilize the negative charge better with its electronegativity. Both of those hydrogens, if they left, they would leave behind a lone pair involved in resonance. Notice a lone pair here with a negative charge is allylic. It's one atom away from an atom in a double bond. And a lone pair here, if the hydrogen left and the bond to it was left as a lone pair with a negative charge, that's allylic too. It's one atom away from an atom in a double bond. So they both have resonance, the equal amount of resonance. So both of those hydrogens are on the same atom, they have the same amount of resonance. What's different about them is the amount of induction. One of them has more electronegative atoms nearby. And that is the hydrogen on the right. This has 2 chlorines. The negative charge would be on the oxygen, only 2 atoms away. Whereas the hydrogen on the left, if this were to leave, it would leave behind a lone pair with a negative charge here. That's 3 atoms away from the chlorines. So the effect would be smaller, the effect of the chlorines on that hydrogen on the left. So the chlorines will work to help stabilize this hydrogen, will work to help stabilize the negative charge on the oxygen better. And so the hydrogen on that is more acidic. What it would end up happening is that hydrogen would leave. It doesn't take its electrons with it. It's acting as an acid, so it leaves as an H+. The electrons in the bond become a lone pair on that oxygen, which have a negative charge. That's partly stabilized by the electronegativity of the oxygen, partly stabilized by resonance. It's an allylic lone pair. And now it's also partly stabilized by induction. The chlorines are going to pull that negative charge toward themselves and help to spread out the negative charge. And if that same process happened with the other hydrogen, if this other one were the one to leave, and the electrons in its bond to oxygen became a lone pair with a negative charge, it would not field the chlorines as much because they're further away. And so we follow the rule that we established, which is that if induction is what you're down to, first you check the two other factors. If those tie, the hydrogen that has the most electronegative atoms closer is the most acidic. And that is this one. That hydrogen is the most acidic. It has the most electronegative atoms closest.